Everybody, Thrasher here. In this video, we are expanding on what we talked about last time. We introduced this idea of momentum in probably a pretty short video. In this video, we're expanding it because momentum is very useful when it comes to things colliding, when it comes to objects interacting. The topic is known as conservation of momentum. That's what we're going to get into. First, just real quick reminder, momentum all by itself is pretty easy. It's the mass of an object multiplied by the velocity. And the symbol we use for momentum is lowercase letter p. So that's important because this video, even though this was introduced in the last video, is still talking about the ideas of momentum. Before we actually get to the heart of the video, it's important to recognize that momentum, like force, depends on direction. And I'll actually start with something else that we learned about way back when that depends on direction, which is velocity. If you remember, technically velocity is speed with direction. And the reason why direction is sometimes important in physics is because it might affect your result or what you expect. Like if you were trying to figure out where I was ending up and I'm driving my car. Obviously, me driving on the highway at 60 miles an hour going north, let's say on Highway 101, my local highway, me going 60 miles an hour north is going to end up with my car being in a very different spot than if I was instead going 60 miles an hour in my car south. So when things are affected by direction, we have to take that into account, at least sometimes. Forces are the same thing. If I apply a force to the right, obviously that's going to cause an object to move in a way that's different than potentially if I apply a force to the left or up or down. And to be honest, team, we've actually used this idea maybe without inherently talking about it. When we did our Newton's second law with net force, we talked about how if forces are in opposite directions, they cancel. It's fine to think of it like, oh, they're just opposing so they cancel out, but also, and from a bit more mathematical perspective, what we would say is just like our number line from math class has positive numbers to the right and negative numbers to the left, in physics, scientists will often say that a force to the right is a positive force and a force to the left is negative. And so if I have the same quantities, but I have like, let's pretend positive 5 and negative 5, that cancels out. So that's another way to think about how forces can cancel. These forces also cancel. It's maybe not as simple as just looking at this number line because now they're acting at a weird angle, but direction matters. Momentum also depends, and it's important that we remember direction. So when objects are going to the right, they have momentum, mass times velocity, but sometimes we're going to see that a little positive sign is going to be included, and that might be important to hang on to. Likewise, if we see an object, maybe in a lab or maybe just in a practice problem, if we see an object going to the left, it's worth noting that that's probably going to be labeled, or that you should think of it as a negative momentum. Again, think of our number line where positive numbers are on the right-hand side and negative numbers are on the left-hand side. This isn't always going to be important, but when two objects are interacting, just like when we had our forces interacting, what direction they matter or what direction they go in matters, and a lot of times we'll do that with positive and negative signs. Okay, I got a little animation. Let's get back into this idea of momentum and the title of our video, Conservation of Momentum. Here I have a set of billiard balls, and we're hitting this white cue ball. It moves down the table, and it slams into these other object balls. Now notice, the white billiard ball has a lot of momentum. It's moving, it has mass, it has velocity, it's flying right here. But look, now all of a sudden it doesn't have momentum. This white ball, the cue ball, goes from having a lot of momentum to all of a sudden none. Here's my question. Where did that momentum go? If you thought to yourself the momentum goes into these other billiard balls, you're absolutely right. This is kind of the core idea behind this video. Momentum can transfer between objects. In the beginning, the only thing that had momentum was this white cue ball. But after that collision, the white cue ball, you could almost think of it like it gives up its momentum, and these other object balls suddenly have momentum, okay? That's our idea. Momentum is a weird thing. It's not super interesting when you just look at the mass and velocity part, but in our universe, when you take those things, mass and velocity, it turns out those quantities can transfer to other objects. That's what we mean by conservation of momentum. Let's read the definition. It starts with this. As long as nothing is getting in the way, as long as there are no outside or interfering forces, somebody like doesn't knock over the pool table, as long as nothing is getting in the way, the total momentum, total meaning you just add them together, the total momentum of objects before they collide should be equal to the total momentum after they collide. That's what conservation means. The word conservation means like to keep or to stay the same. For conservation of momentum, the idea is that the total momentum doesn't change. It can go from one object to another, or again, in this example, we have momentum going from one object, the cue ball, to multiple objects, but the total amount should stay constant. Whatever momentum this cue ball has, let's make up a number, let's say it's 10. Well, I can't really do it in this animation, but if I could pretend like I added up the momentum of this ball, the momentum of that one, and the momentum of that one, I should also get 10 in total. The momentum transfers, but the total amount stays the same. That's why if you hit the cue ball harder, you'll often break these balls better. More momentum before can transfer to more momentum after, but the total amount is staying the same, okay? So let's see it in words. The initial momentum of the cue ball is equal to the total momentum of the other billiard balls after the collision. Again, we're talking about before and after. And the before momentum, this is an important word, equals the momentum that we have after. Okay, the momentum we have in the beginning is equal to the momentum at the end. You could write it as an equation, and it looks kind of silly just because it's like P equals P. But this is what it's saying. The momentum, let's say in the beginning, or the momentum initially, must be equal to the momentum after, the momentum final. You could totally write it like this. You could also write it like PI for initial and PF for final. Totally fine. I will say, and I'm sorry, sometimes scientists do silly things. When it comes to momentum, sometimes scientists like to write it like this, where it's saying the same thing. The momentums are the same before and after, but now they'll use this apostrophe. This is read as P prime. Not super important, but you might see it written this way, either in practice problems or in online resources or in textbooks. This means the same thing, and I'm sorry they're not super consistent, but again, what's the idea? Whatever momentum we have before should be equal to after. And when I say before and after, I mean like some collision or some interaction, okay? That momentum is staying the same. Here's a type of collision, and there's dozens of different types, so there's not just one particular example. Here, maybe this ball is at rest. I have this larger ball rolling in, and it collides, it hits it, and then after, the two continue moving. Maybe this ball was kicked very quickly to the right, but this larger sphere keeps on moving. It keeps chugging along. Again, the total momentum before should be equal to the total. Like I look at this guy's momentum, I add it to this guy's momentum. They should add up to be the same amount, okay? Let's look at an example. And this is kind of a collision. It's maybe the opposite of a collision. Let's think of this as a bomb scenario, okay? I have a bomb and it's starting at rest, okay? Starting us off, what is the momentum of the bomb right here? I've lit the bomb, but nothing is moving. What is the starting momentum of this bomb? It's 0. Remember, momentum is based on mass, and yeah, the bomb has mass. It's also based on velocity. The bomb is not moving. This object has 0 velocity, so the momentum has to be equal to 0. Okay, then let's say, oh my gosh, the bomb explodes. But for this problem, it's a really bad bomb. It's just breaking into 2 pieces. That's going to keep our lives a little simpler. So it starts as 1 piece, and then it breaks off into 2 pieces, okay? So we started off with 0 momentum. All right, nothing is getting in the way. Nobody's knocking the bomb off the table. If I started with 0 momentum, and if momentum is conserved, what do you think the total momentum is after? It's 0. That's the idea. That was our definition. Again, the definition says as long as nothing gets in the way, the total momentum we have in the beginning should be equal to the total momentum after. I know now we have pieces moving, and we'll get to that. but the total momentum should be staying the same. This is an example of applying this idea of conservation of momentum. Let's go one step farther, because you probably notice that now the bomb pieces are moving. Let's say this bomb piece, it's flying to the right. Let's say it has a momentum of 5. I just made up a number. But let's just pretend if this momentum is 5, what does the momentum of this piece have to be? Maybe a little tougher question. Again, the total momentum needs to be 0. Total meaning when we add up the momentums, it should be 0. So if I told you that this piece has a momentum of 5, the momentum of this piece has to be -5. Why? Because -5 plus 5 gives us 0. Do you see? We kind of have this puzzle going on. You can learn some things by the idea of momentum staying the same. So if you know the momentum before, that is the momentum after. And since this is by definition the total, the pieces need to add up to equal that total. We'll see some practice problems, certainly if you're in my own class, and probably if you're doing this for another class or another course that you're taking, okay? But little puzzles based on this idea that the momentum in the beginning should be equal to the momentum after. The last thing I want to do really is just explain the same thing in words. I kind of said it out loud, but sometimes it's helpful to see it written down, okay? The bomb starts at rest with 0 momentum. Remember, momentum is m times v. So no velocity means 0 momentum. By conservation of momentum, if I started with 0, it must have 0 total momentum after it explodes. That's how I determined this piece. Well, and sorry if my head is kind of in the way, if I add up the momentum of the individual pieces after the explosion, they must equal the total they had before. Again, the total before was 0. So the total after is 0. So when I add up these pieces, they have to add up to be the total. Remember, that's what total means. You add them up. Okay? So we use the idea of conservation of momentum to figure out what the momentum is in total before and after. And then like a little puzzle, you could kind of figure out what the pieces have to add up to be. That's the idea. Again, in my own class, we'll do some example problems of this where you kind of analyze based on this idea of momentum staying the same. It's all based on this idea that whatever we have in the beginning is what we have in the end. And then you might see, depending on the class that you're in, some slightly tougher problems because remember, momentum itself can be broken down. Momentum is, again, mass times velocity. But that's it. Our idea is that the total momentum of objects stays the same, even if there's multiple objects colliding. But if you look at the total, the overall amount before, it should be equal to the overall amount after. All right, thanks for watching this video. See you next time.